Thank you, Ken. And thank you for coming to the live session. I recognize many names that, well, I see many names that I don't know. So it's great to see new faces or new names popping up into this session. I guess I've been really keen wanting to do something on Sentinel-1 for a while because we've made Sentinel-1 data available, and I've been really wanting people to try to make use of this data, and it's kind of a new data set as well. Most of the people are more familiar with the optical data that's widely available, and Sentinel-1 analysis ready data is quite new. So the point of today is really just to get this started, having a very brief crash course on how I understand, what I understand SAR data is, and give a couple of recommendations on how people can go explore the SAR data. The first couple of slides will be quite going into the details, but I think, you know, my background is a physics, so I prefer to understand why before I do a lot of things. So bear with me. It's perfectly okay that you don't get all the details. It's really just to set the scene, that making sure that it's clear that the SAR data, working with radar data, is very different to optical. So kind of you change into a different mindset of how you understand the data. So to start, the synthetic aperture radar sensor that we work with, these are active sensors. So by that, it means that it emits its own signal, microwave signal, and then also have detector to receive the signal. So it measures the amount of signal received. And that means because it depends on the signal it sends itself, so it works day and night, although the sensor we work, or the Sentinel-1 dataset we work with, always collect data in the day. But in principle, a radar sensor can work at night as well. And the other thing is, it's the reason it's called synthetic aperture radar. It's not a real imaging device. What it does is sends out signal and receives it back and reconstruct the signal to make an image. So the way that it does this, you know, it knows about where the signal has bounced back is through the measure of the delay time. So if the surface, if it's mapping a target that's further away from the sensor, it takes longer time to come back, so that it knows the signal has been bounced back from a surface or target that's further away. So that's how it knows about where the signal has bounced back. And that also means the radar sensors are always side looking. So it's looking to the side, because if you're looking down directly to the Earth, it takes the same amount of time for a signal to coming back from the left side compared to one from the right hand side. So the sensor actually can't decide where the signal is coming from. So it's actually, these radar sensors always looking to the side. That means also that if your flight direction changes, you're looking at the target from different, you may be looking at the target from different angles. So if, you know, instead of flying out of the screen in this image, if you fly into the screen, but still looking to the right, for example, then you're looking from a different angle to your target. And this is how Sentinel-1 works. When its fly path is different, it's actually looking at the target at different angles. And it depends on a DEM to know where, of course, if you have a heel here, you know, it changes that geometry so that the target return time will be affected, so that you need a DEM to understand where exactly your target is on the ground. And that also means that if you have a tall target or a DEM that's inaccurate, you might have artifacts in the images. So sometimes you see these odd features in the image that can't be explained, and it could be due to these artifacts. But of course, the goal for us is to provide the data processed as clean as possible. So do all the corrections as the best way we can, so that the users don't have to worry too much about these. It's unavoidable that there's still some leftover effects in the data, but we want to provide an analysis ready data set, which means the data we provide is the normalized radar backscatter. So what does this term mean? So we actually have Sentinel-1 backscatter and also ALOS annual mosaic that's collected by ALOS pulsar and pulsar 2 sensors. So both of these data sets are normalized backscatter. What does that mean? Is so by backscatter, that just means we only have data that measures the amount of microwave that reflected back from the sensor from the ground surface. So this is only an intensity measure, but at the sensor. And by normalization, that means this measurement or value is normalized to an area perpendicular to the line of sight. So it's called gamma null. There are different ways how you can normalize the radar data, but this is really so that if you normalize to the same area, then you can compare signal from different area and different look angles. And the other thing that is required by the CEOS analysis ready data specification is that the data is radiometrically terrain corrected. That means the effect of terrain and sensor geometry have been corrected for, so that if you have a mountain that's kind of been flattened, so that the effect of that mountain has been reduced, and you look at the image, it's mostly flat. You would still notice some artifacts left over residual effect, but for the most part, the terrain effect has been mitigated. So the images are mostly comparable. And I think, well, although we have two different data sets in DE Africa, but the more the one that I think is more significant and we're hoping to do a lot of application with is the Sentinel-1. So for those that are not particularly familiar with Sentinel-1, it collects radar signal in C-band. So this means that the wavelength of these radar signals is about 5 centimeter. So this is actually, you know, quite sizable wavelengths, so that anything that's if you have a surface or structure, so it kind of goes through really big gaps of leaves. So the data that is available in DE Africa or in the data cube sense is when you load data through ODC, this is the S1_RTC product. This means this is radiometric terrain correction. So RTC means radiometric terrain correction. So this is the name we use for the analysis ready data. And the other thing is the data coverage we have is actually from July 2018. This is partly because we were hoping to get more data, but it turns out that the data volume and the coverage over Africa is more than what we initially expected. So we decided to restrict to only start July 2018. So we roughly process the same amount of data, but if there's a need, we will pretend, you know, in the future, there might be a possibility that we will get more data back earlier, because so the Sentinel-1 coverage actually starts somewhere from 2014. And we're hoping, of course, that ESA will be providing some of these data sets for free in the future. So over Africa, roughly the data coverage is every 12 days. However, if you look at this map, the darker squares means there are more images available for these areas. So you can see that the coverage over close to Mediterranean along the northern coast is actually really good. So every few days you actually have a Sentinel-1 acquisition. And then there's also increased coverage in East Africa, and these areas are actually covered by 2 different look angles. So there's these if you squint, you can see the path pattern. There's the path is going this way from northeast to southwest. There's also passes going the opposite direction. So one of them is ascending and one of them is descending. So some of the areas are covered by both orbit directions, so it gets better coverage. And we mix Sentinel-1A and 1B data. For the most part, the calibrated data are quite similar. So Sentinel-1 actually observing multiple observing modes, so they have different sensitivity and spatial resolution, but the most common one used over land is this interferometric wide swath mode. And so we decided to only provide or process data in the IW mode and with both VV and VH polarization. So the polarization designation means that the VV means the signal is emitted or emitted by the sensor in vertical polarization, and then it also received as vertical polarization. And then VH means the signal is sent as vertical, but received back as horizontal polarization. So the polarization has changed along the way. And of course, we also have ascending and descending images. And because Sentinel-1 only look to the right, so the ascending and descending passes cover the land surface from different look angles. And the other thing that's worth mentioning is in addition to the backscatter in VV and VH, we actually also provide additional, additional bands. So include a data mask. So this is really just whether a pixel is a valid or invalid, and this is mostly due to radar shadow. We also have the scattering area that's actually used for the normalization. So this is probably for more expert users if you want to really understand what correction has been made to the image, if you want to weight the image in some way according to the scattering area. And the other thing, because look angle is very important, we also have a band that has the local incidence angle. So this is an image, so per pixel local incidence angle. So you can use this as additional information to tell you why the signal, to interpret the signal. And I guess there's a lot of physics behind how the radar sensor work, but I just want to focus, I want to give a little bit of explanation, but also focused on the applications we often say the radar sensor is good at. So I'll start with water. One of the big interests in using radar sensors detecting surface water, and this can be just open surface water or flooding. Now, radar is really great detecting water because a water surface appears flat to the radar sensor. And if you send a signal to a flat surface, it gets reflected away. So it basically, very little signal reflects back to the sensor. So that's why water surface looks very dark in radar images. But if you have a rough surface, so vegetation, soil, anything that's rough compared to the 5 centimeter wavelengths, then your signal gets scattered into all directions, and some of the signal will be reflected back to the sensor so that you have an increased signal. But this also means that if you have if you have roughness in the water surface caused by wind, for example, then your water doesn't appear dark anymore. So that would cause some confusion. The other thing that might happen during flood is this effect called double bounce. So if you actually have two surfaces at a right angle, what happens is the radar signal reflected once and reflected twice and happen to be mostly in the incoming direction. So then you get lots of signals reflected back. So this also happens in urban environment where you have lots of buildings, or if you have trees standing in water. So anything that gives you that rigid right angle that might lead to an increased radar signal. So if you look at radar signal over a city, you see lots of bright pixels, and that's because of this effect. So that can also be used to detect flooding in urban area, for example. And the other thing radar is good at is measuring or track changes in vegetation. So for over vegetation, there are lots of different ways that the radar signals can be reflected or scattered. So sometimes it's just reflected back from the top. Sometimes you have double bounce effect actually, but you can also have signals that penetrating through the trees and then also gets reflected back. So actually the longer wavelengths the radar signal is, the better it is, the more likely it's going to be penetrating through the tree canopy. But you also have these signals that's, if you have lots of leaves, the signal would just bounce between the leaves, and eventually some of them will be reflected back. So this is called volume scattering, because you have lots of complicated scattering happening within that canopy. So then you can imagine that if you have a crop, for example, when there's only when it's just sowed, there's a little structure, so you probably don't have much volume scattering happening. But then as the plant grows or the crop grows, you have more leaves, and that leads to a change in the backscatter signal. The other thing that radar sensor has been used to measure is moisture content. And the reason for that is it's not just geometry, but also when the radar signal interacts with the surface, the dielectric constant of the surface affects how much signal is reflected. And when there's moisture content in the surface, that reflectance is increased, so that if you have a wet soil, the signal reflected is much higher than when you have a dry soil. So if we put all of those together, very roughly or conceptually, you can have some idea of the intensity of the radar backscatter over different type of surfaces. And mostly this is affected by geometry and wetness of the surface. So as we just said, if you have a flooded surface, because it's flat, signal get reflected away, it's really dark, you have very low backscatter. If you have dry soil, so it's not as smooth, so you get some signal reflected back, so you have increased backscatter. But then if you have a wet soil, not so wet that it's just completely flooded, but if wet enough that it increase the backscatter, it increased how much backscatter is reflected, then you also have increased the signal compared to a dry soil. And in some complicated environments, for example, wetlands, you have lots of different conditions. If you have an inundated tree, tree trunk standing above a flat surface of water, then you have the double bounce, gives you a very strong backscatter signal. You might have standing grass, which, because it's less rigid and not all the grass is vertical to the water surface, it can still give you quite a strong backscatter, but not so much. And then you might have trees, because of the volume scattering in the tree canopy, you have quite high backscatter. And then dry grass gives you a bit lower, and then bare soil, because it doesn't have that canopy structure anymore, or any leaf structure anymore, it's pretty low backscatter. Most of the signals are actually reflected or scattered away. And then of course, lastly, you have the surface water or any very flat surface that will give you very low backscatter. So that's roughly how you can, based on the signal, determine what might be happening. But of course, then this is all relative. So if you have in the same scene a different signal strengths, this might be what's happening. But for different areas, an absolute scale doesn't mean that a low backscatter is always surface water. It might be caused by other flat surfaces. And the other thing that that's typical, what can be done with Sentinel-1's multiple polarization or dual polarization, is use that relationship between the different polarization to measure, to understand the scattering mechanism, especially over vegetation. So we don't have, this is partial information, because we only understand when the signal is sent in vertical and received back in vertical and horizontal, what happens in these two different combinations. But when you have the VH combination, this means some depolarization has happened. And this depolarization does depend on the scattering mechanism. And most of this, well, especially for the vegetation area, most of this might be caused by volume scattering. And if you look at the radar images, you would also notice that VH usually has a much lower intensity than VV, so that most of the polarization stay the same, and some signals has changed the polarization. So this also means that over vegetation, the amount of leaf structure can be approximately measured by just the VH backscatter, or if you want to be more accurate, you know, you can do a lot of different things to try to understand the relationship. It could be the ratio, it could be the radar vegetation index is really just measuring the VH signal relatively to the strength of both the VV and VH. And there's other combinations you can do, combining VH and VV to understand the relationship that gives you different, I guess these different types of parameters might be optimized for different type of vegetation or surfaces that you're trying to look at. So some of these indices, we call them indices in kind of the optical language. We've implemented them already in the Digital Earth Africa tools in the Sandbox repo so that people can use some of these. And just to give you some example here, this is comparing for, I think, for over some rangeland area, the radar vegetation index entropy. This should be very similar to the pseudo entropy that's calculated from our data compared to the NDVI measured from optical imagery. So as you can see, they actually correlate pretty well with each other. But then, of course, NDVI is measuring optical spectral response. So this is actually measuring very different things. But because this usually correspond to, say, leaf or grass grows, so that it's actually correlating with the radar vegetation index. And when you have more grass or more green structure, you also tend to have more structure that gives you higher radar backscatter. And before we move to the applications, if you've looked at some of the radar notebooks, you would also notice that there are a couple of pre-processing steps sometimes are done. One of them is to do with the speckle noise. So this image on the right-hand corner, it's actually just over a homogeneous area, but as you can see, the signal is not smooth. You actually get lots of salt and pepper effect, which is called the speckle noise. And this is typical for all the radar images. And that's actually interference from unresolved scatters within each pixel. So this is there's no way to avoid a speckle noise. But what you can do is, because it's a noise, it has a certain distribution. If you average over multiple pixels, whether it's spatially or over time, you can actually reduce the amplitude of that noise and give you the true underlying, a better measure of the true underlying backscatter signal. So just showing the effects of two different popular speckle filters. I think some of the Lee filters actually implemented in some of the example notebooks. So this is the original image. As you can see, especially over water, because water has very low signal, you can see that there's actually quite a lot of noise. There's the brighter pixels within water. So if you implement a Lee filter, what this does is it's kind of taking a windowed, so within a small moving window, it's doing some sort of mean, but the way that it's doing it, it's not a simple smoothing moving window mean. It's also accounting for the local variance, which means it's better at preserving the edge. So even though you can see clearly that image has been smoothed, and so the resolution kind of has been reduced because you're averaging over multiple pixels, the adaptive filter actually allows you to preserve most of the edges in this original image, so that you can see the image is a bit blurred, but you do have a reduced noise inside the water, so that it's actually a bit smoother and enhance the contrast between water and the land surface. And the other option that you can do is to filter over time. Then you're really just taking an average or a weighted average from multiple images that collect at different times. So all these different filters. So in this case, of course, it preserves the resolution of the image, but then it can be problematic if your underlying feature is actually changing over time. So, and there are a lot more different type of speckle filtering or adaptive method that can be used, and each one of them is slightly different and can have their own pro and cons depending on what signal you're actually trying to preserve and trying to detect. But the leaf filter is usually relatively easy to implement, and it works reasonably well for most of the applications. The other thing people always do when doing analysis for with radar data is doing the decibel conversion. So this is just a log transformation. As you can see, the formula is really just doing a log transformation. So it's not really changing the relative strength of the signal, but it changes the distribution. So this is an image, I think, with a water surface. They're giving you the low backscatter and then some land pixels. This is in the original linear intensity measure that's provided in the data. As you can see, the distribution over water is kind of squashed because it's very small. And you have this very asymmetric distribution of kind of noise in the data. But if you do the log transformation, it expands and changes that distribution, and your profile and your noise is much more symmetrical. So if you if you run a statistical model, a lot of the times that your model would assume that you have a symmetric Gaussian noise, for example. So then it would be more appropriate to use the log scale signal in your analysis rather than the original intensity ones. And I was just to go through a couple of examples that we already provide in the notebook repo, and trying to tie back to what I've just explained and see if that makes more sense. So the one of the examples that we provide in the notebook repo is the water detection. So I think this is actually over a wetland area, so it's actually quite complicated. So you have the open water surface that looks quite dark, but then there's also kind of the seasonally inundated area that changes from time to time. And then I think there's a bit of a city or urban area next to the river, so that it gives you the high signal. These two images actually have been already speckle filtered. And as I said, over these areas, after you've done a speckle filtering, your contrast between the low signal and the high signal has increased, so that you don't see that speckle effect as much within the water body, for example. And over the land, this noise has already also been reduced. But of course, then it looks a little bit smudged because of that smudging, smoothing effect. And the other thing that it's recommended doing for these water classifiers is doing the decibel or log conversion, because once you've converted into log, you have the nicely distributed two-peak distribution in this case, where you can decide where to put a threshold filter in, and then you can really let you reasonably cleanly separate water from the other surfaces. And then we also have a ship detection notebook that was the result of one of the ODC hack event. So in this example, if you look at these images, all these bright spots are cargo ships. And the reason for that is this is the Suez Canal. So the reason for that, if you think back on what we've just talked about, this is because these big ships have rigid structure, and they have containers on top, they have structures, so that gives you all those right angles, and then lead to high backscatter signals. And if you look closely, actually, if you zoom into these, it's not just one dot, it can be multiple dots, because there are so many structures on board these ships. So it's actually quite tricky to cleanly detect a ship. But in the notebook, what we've implemented is a very basic thresholding, just to say, compared to the dark water surface, the ships really stand out. So we can cut on the threshold to detect the ships. And the other cute thing that you can do is, of course, if you take the maximum over time over water, everywhere that ship has ever gone through would have an elevated signal, so that if you combine over time, you can detect where the ship has been, or the shipping lane, or even the parking spots for the ships. So just want to mention that. And the red hot new thing that we did today, because we also had an internal workshop today for Sentinel-1, in this phenology notebook. I've wanted to have this for a long time. This one is still, I think, in a branch. It hasn't been merged into master branch yet, so it's not by default loaded in the sandbox, but it is available in the repo through this link. Chad is still working on this, so be aware that this might disappear someday and be merged into the main branch very soon. What this is doing is actually, if you're familiar with the phenology notebook that's already existing in the sandbox repo, that's using the optical either NDVI or EVI, and looking at the seasonal changes over time and try to measure in the start of the season, peak of the season, some of these phenology parameters. This is replacing that with radar vegetation index. And as you've seen previously, this correlates really well with NDVI. So you see a very similar trend, and then you can use the radar signal less affected by cloud to track how the growing seasons and what's the pattern look like. And this is the per pixel phenology plots. That's just the same one as in the optical notebook. However, you also notice that this has been masked. So this is actually only looking in the crop mask region. So this is also combining the newly developed crop mask that's available, because if you include every pixel in that area, of course you have all these things happening outside of the crop, and we don't care what is going on there. So combining the crop mask, we can really only focus our analysis in where the crop are planted, and then see the seasonal trends over these crops. And as you can see, this area is quite homogeneous. I think most, the planting time and peak of the season is quite similar for the whole area. And that's probably the last of my example. And the other thing that I just want to mention is that working with radar data can be a bit overwhelming, because it's not intuitive at all compared to optical data, especially if you've been working with optical data for a long time. And even for me, I don't always understand, looking at the radar data, I can't be quite sure what is going on. And it's very normal. It's a bit scary, but it's very normal. And we probably just, all be there, and really we just need to try, and slowly we'll understand what better these data sets. So if you're interested in using the radar data, I'll highly encourage you to go to the map portal to see user visualization, because if you can't see a feature, then it's less likely you'll be able to detect with an advanced method. Although there's, details in there, but the very first step, if you want to see what radar data can do for my application, is go to the map, use the standard visualization. There's single band as well. This is RGB, combining the different band and ratio to enhance the difference between the different features. So, have a look and see whether your area of interest or the features you're interested in is actually detectable by the radar sensor. And then it's really helpful when other data is available to help you understand what's the radar, what's the story the radar data is telling. For example, the optical data, if you're familiar with the optical data, find an image that's from the similar time, but in optical, and see if you can link the features you're seeing in radar to optical so that you understand what's the relationship. Use ancillary information, and ground knowledge is really important as well. If you know what is going on in this area, if you have ground data, then that will really help pin down that, or understanding that radar data set as well. And always keep in mind, viewing geometry, roughness on the couple centimeter level, because similar to the wavelengths of the Sentinel-1 sensor, the roughness at a couple centimeter level and also wetness really affects your signal. So if you see a change, or a difference in the features, that might be because of one of these reasons. And of course, a lot of the approaches, you can always do a machine learning or black box approach, throw the data at a model and see what happens. But if you understand all the geometry and the details of the physics behind the model, then of course there's a chance that you can tune these models to work more effectively. I guess I'll leave it there and give people a chance to ask questions. And does anyone have any questions for what I've talked about so far?
Thank you very much, Dr. Fang, for this great presentation. It was very good to have the overview, and I've put a small example for our colleagues from Rwanda who've joined, and also the others will be able to give you any area they would like just to get us started.
Yep, that's awesome. Yep. See, someone had a question. This.
Hi, Dr. Fang.
Oh, yes.
Sorry.
Okay. Yes, I had a question. I really liked your presentation.
Thank you.
Okay, so I had two questions. One was when you were talking about the various properties like a wet area and a hilly area. So one of the things using radar a lot is the shadows that appear in terms of when you're using a hilly area and also when you're using wet areas. What would be the probable advice in terms of using reflectance in such particular areas? And number two, maybe the last question, when you're comparing the vegetation indices, which I really liked, there's one analysis we're doing with Nana Edward, and I wanted to ask, is there a difference because I've seen various literatures use NDVI in radar. However, when you were comparing the formulas or the way they were using their formula index is the same as the one that's been mentioned in the radar vegetation index. So just to confirm whether it's okay to call it also an NDVI for radar, or it's suitable to have it as the radar vegetation index based on the sample that you presented.
Yeah, I'll probably answer the second one first. I mean, the terms used in the radar community is confusing, I think, to my mind. I mean, I feel like it's just a term. Someone invented it and called it radar vegetation index. So the original radar vegetation index is actually using the CODPOL. There's a CODPOL definition as well, and someone simplified it and has a, there's a proxy using just a dual polarization. So I think all these names are just, history of who invented them and what they happen to be calling them. And there's the more complicated ones like the normalized, because you can also do the normalized index way. I think that's one that you've used in the notebook that Edward showed me. So yeah, so you can do it in a normalized index style. It's still valid. It's just, people call it different things. So I think it's confusing, and that's why if you're using analysis, it's always good to, I don't really know what's the resolution there, because all you can do is always make sure that specify what formula you actually use, and if you're really reading the literature, really just quoting and make sure that you use the same formula that they actually quoted, because people call them very different names, and there's lots of different combinations as well that give you slightly different result. And as I said, because there are only two bands that you're working with, so a lot of these different measures give you quite similar result. If you go, if I go back to that example of comparing radar vegetation index to entropy, for example, for most of the times it's actually quite comparable, but then there's some details that's different. So I think, well, because they are doing different calculations and tracking different relationships, so what typically happens, I think, is when you have a specific type of vegetation that you're trying to map, for example, a certain type of crop that has certain type of leaf structure, then it might be useful to explore these different parameters or different combinations to see which one is happen to be more sensitive for your specific application. But for things that have changed quite significantly, or in a generic sense, you want to understand vegetation change, then using any of these, vegetation, the radar vegetation index here, or even just using the ratio or VH, kind of gives you a proxy measure already. Does that answer your second question, Stella?
Yes, perfectly. Thank you.
Yeah. And on the first one, I think it's probably more tricky for the hilly area and the shadow area. So as I said, the radiometric terrain correction tries to correct for that, that effect of terrain, but things that it kind of can't correct for is if you have a flat surface. So if you have vegetated, so let's say if you're in the mountain forest, right? In the forest, because the scattering is going everywhere, it's volume scattering. So when you look at the trees from different angles, you should be getting roughly the same signal back. So if you correct for the terrain, then you should, your resulting image should look quite flat because your terrain effect has been corrected for. So that's really correcting for the intensity difference between, the length of the, how far the signal has traveled. So you really correct for that. You can really correct for the terrain so that it looks roughly flat. But if you have a flat surface, there's other geometry effect that you just can't correct for. So in those cases, that's just a limitation that you're kind of limited. If you have a flat mountain top, one side of your mountain might always look slightly different. And the other thing is, the limitation of that correction is also it does change the effective spatial resolution of the data as well. So even though the signal looks more or less flat after radiometric terrain correction, the effective spatial resolution is actually still different on the two sides. So there are things that can't completely be corrected for. And that means in your analysis, change detection, for example, for radar, that can be particularly useful because if you're tracking a pixel through time, for example, that change over time probably will give you more information than say how this pixel compared to the other, because the other pixel might have different looking geometry. But if you track how one pixel changes over time, that might still give you information on how things have changed. So yeah, there's no simple way of dealing with this. I guess, yeah, what you can do is really look deeply into the data in all these different ways, really look at individual observations and see what patterns you see from observation to observation, what patterns is consistent over time, and really depend on your application. There are some generic approaches, but if you want to get really good results, then sometimes you really have to look at on the application, your area of interest, and how to, yeah, might be, you might just need to be innovative in coming up with different ways of dealing with the data. So unfortunately, that's a bit of a limitation for a lot of the applications. You might have to really investigate and understand the local environment than relying on generic method. But then, of course, there are also other things that can be generic. So yeah, I hope that helps a little bit. But yeah, there's no simple way to dealing with radar data. I guess that's the bottom line. I think someone else has this question as well.
Hi, Dr. Fang. Hello.
Yeah, you go ahead, Corey.
Yes, thanks so much for the presentation. At least now I get a gist of Sentinel-1 and how it works. It has been so hard for me to wrap my head around Sentinel-1, but I think we've introduced it. And I think from here on, it will be easy for me to know more. Now, I just have two questions. The first question is about classification. You know, when we're using optical data, we are using spectral signatures to do a separability analysis. Now, when we're using Sentinel-1 data, can we use it as a standalone to do a separability analysis? Can the backscatter signals be used to, for example, when you're talking about crops, can it be used?
Yep, absolutely. So it has different physical meanings and relationship between the different bands, but absolutely you can do that separability study using VVVH, and I recommend adding additional, for example, ratio one, or like a one that combines the two. But yeah, like you can use all these as features. There's just the correlation between these features will be different compared to optical, but definitely you can do those analysis, and in that black box, somewhat black box approach, I guess, a lot of the applications would just try to add as many features as possible. At some point you becoming degenerate, and the new features you add don't add a lot more information, but definitely you can use individual measurement VVVH, and you can use all of these combinations of bands as your features in your model.
Okay, thank you. Thanks a lot. The second thing, the main takeaway that I took from this presentation is that for Sentinel-1 data, it depends mostly on one, geometry, roughness, wetness.
Yep.
So when it comes to image processing, does it give us a way or a door for us to carry more research on how probably we can use deep learning algorithms, segmentation, and probably CNNs and all that to do an image processing, so that we can be able to classify this Sentinel-1 imagery?
Yeah, absolutely. I mean, all those that I explained are really just what has affected your signal. At the end of the day, you might not have to understand explicitly what has happened, and very much similar to an optical image, right? Like you kind of know what NDVI is measuring because that the chlorophyll signature, or there's a physical meaning behind those, but when you looking at the image structure, those physical meanings, there are different ways of using those physical meanings. If you look at the image structure, it may not be as important. You're really trying to detect, one, you can imagine this is an optical image as well, because when you do image classification, you're really just separating different types of pixels. So why this pixel appears brighter compared to the other may not be as important. You're really just trying to distinguish the different patterns or features. So you can definitely do that over SAR image as well. And actually it's very popular to use deep learning to classify SAR images. I guess the complicated was so similar as in using optical images. If you know what are causing the differences between your optical spectral response, then you can sometimes adapt your model to consider those. So it's the same as radar. If you know what is affecting your signal, then you might be able to tweak your model a little bit, or your machine classify a little bit, so that it works better for the specific type of imagery. But a lot of the times you can definitely use the standard method for image classification. Now, if you do use the classifiers kind of works on images directly, you do have to consider speckle noise, or it kind of affect you a little bit, because that's additional noise added to your model. So, but it works the same, like, there's noise in optical data as well. In radar, there's just increased noise. So, and it probably, for many of the methods, you don't even have to care. It's already considered in the model itself. So I guess it's just it's case by case. You can definitely explore different machine learning, deep learning, classifier, image classification, or computer vision models on SAR images. There's no limit to that. And it's just that if your model doesn't work very well, if you want to fine tune your model, sometimes, go back to the first principle and might help. That's all I'm saying. But yeah, you can definitely use them.
Thanks a lot, Dr. Fang.
So thank you very much, Dr. Fang, for this great presentation. I think, is there anyone else before we do a group photo to commemorate this important session? Also, apologies for the technical hitches in the loading of some of the data. Possibly there was some filter.
Yeah, I'm not sure why.
Maybe there was a filter somewhere in one of the filters.
And I have a quick simple.
Oh yeah, it's coming up.
Yes, Dr. David.
Yeah, thanks, Dr. Fang, for excellent presentation. I'm not a person who has used these tools, but I'm interested to know if we can apply this. For example, I'm doing some experiments at plot level, and we are looking at the phenology. And we are talking about trees which are still quite young. And I just wondered if this can be applied to follow through to look at the phenophases like flowering, leaf shading, and all that stuff. Is it at a scale which we can use this tool?
Flowering and yeah, possibly. Yeah, so that's the trickiness of this radar imagery. If you have, so I would recommend if you have an area of interest, you can try. Go have a try of the phenology notebook and see if you can see the subtle changes. Because there's these geometry effects that gives you a little bit of noise, because when you look at the things at different angles, the signal changes a little bit. So depending on what level of change you're trying to detect, I mean, on top of my mind, I don't know how much those changes that you're talking about, how much changes it actually leads to in the radar signal, but you wouldn't know probably until you've tried it. So I do encourage you to, if you want to know it, just run it and see if you can actually detect those changes that you want to see. It might be obvious, it might be washed away in other signals. So yeah, so I don't know, but I think it's worth trying.
Great. Yeah, thank you. Excellent.
Thank you so much, Fang, for responding positively. I know it would look like it was another PhD thesis or defense. Sorry for these many questions, but this is a very new.
No, that's great.
Yeah, thank you so much.
Questions are good.
We could have our